Okay, so this is chapter 2, stuff like that. So we're going to be talking about how things are arranged in space, stuff like that. So the first thing we're going to talk about is what's called Vesper theory, stuff like that. So this is valence shell electron pair repulsion theory, and basically what it allows you to do, and hopefully you would have been introduced to this in the in general chemistry. It is basically again how the atoms want to arrange themselves in space, stuff like that. So. There's a couple of different rules in this, stuff like that. So I'm not going to ask you like, what's rule number 2? But there are things that you need to remember in order to be able to solve these problems. Okay, so the first thing is that what we have are what we can loosely term as groups. Okay, stuff like that. So lone pairs, then any bond type is considered a group, stuff like that. So let's say you have, so say something like. A molecule like this. Okay, so here this nitrogen, okay, it has 1, 2, 3 different groups. Okay, so a lone pair is considered a group. A double or single bond is considered a group. A double bond is considered a group. It's not 2 groups is when. So this guy here, this has 3 groups around it. Okay. Same with this carbon here, right? It's going to have 1, 2, 3 groups around it. Okay, so it's going to have 3 groups as well. Okay, so with that, but remember the single, double, triple bonds, stuff like that. They're all each going to be considered a group. Stuff like that. So, okay. Next rule is that things want to be as far apart around the atom as possible. Okay, so with that, so we've all seen this with the in an elevator. When you get in there with people you don't know, what happens? People just naturally gravitate as far away from each other as possible to give as much personal space as you can with that, and that's what atoms do arranged around a molecule, stuff like that. So. Okay, so if there's 4 people in here, they'll go to the 4 corners. If there's 3, then they'll either one go to this corner, but usually somebody will sit here and stuff like that. So they'll arrange themselves to that. That's exactly what happens with atoms around an atom, or atoms attached to another atom. They're going to rearrange themselves. Okay, so the electron density, or the electron geometry. Okay, these are sort of like the base structures. Okay, so with that, so if you have just 2 groups around it, the base structure is going to be linear. If you have 3 groups, you're going to have, it's this trigonal planar. Okay, with linear, right, this bond angle is 180 degrees. With trigonal, it's 120, and then with 4 groups around it, it's going to be tetrahedral. Let me go grab them all. So here, so this is the tetrahedron, okay? So with that, so you have them arranged as far apart as possible around that, around the central core, right? So if you have 4 groups around here, the central atom is going to be this tetrahedron. So with that, with this bond angle here being this bond angle here and here, going to be 109 degrees, stuff like that. So, okay, so those are sort of like the base structures. Okay, the molecular geometry. Okay, so what basically happens there is you take your base structure, and wherever you have a set of lone pairs, you basically cover that up. Okay, so like that, and so the so with molecular geometry, you're only talking about the atoms. Okay, so like that. So if you have a tetrahedron structure and you cover up one of the lone pairs, what you're going to be left with is what looks like a very flat triangle, and we call that a trigonal pyramidal. Okay, it's like a triangular pyramid. If you have 2 lone pairs around it, 2 sets of lone pairs, you're going to end up with this. And so 2 of these base structures, 2 of these for the base structure covered up, and so it ends up being bent. Okay, stuff like that. Same thing with the. Let me see if I got it here. Okay, so here's a trigonal trigonal planar, right? So they're all in the same plane. If you have 1 set of lone pairs, right, you end up with something being bent. Okay, it's just a bent structure. Okay, that's all you got to do. So if you remember the base structures, okay, and then just cover up where lone pairs are, you'll automatically know what the structure is. Okay, so again, with that, right? So if you had this, again, we're going to go back to this structure. Okay. So what I'm going to do is I'm going to say, okay, what's the molecular shape, the molecular geometry, the shape around these atoms? Okay, and I'll have big arrows pointing to them. Okay, so for here again, we have three shapes or three groups. Okay, for this one here, so the base structure is going to be this trigonal planar. Okay, but this group here, right? So this group here is going to be a set of lone pairs. So we just kind of cover that up. And so what does the structure look like now? Well, it looks bent. Okay. Now for this carbon, right? It also has 1, 2, 3 groups. Okay. So the base structure is trigonal planar, but we have atoms at all 3 positions. We don't have any lone pairs, so it remains trigonal planar. Okay. Okay, so next up, with that, so the this 190 degrees, so with that, or if you have a double bond, it's 120 degrees. Okay, if that's really where it wants to be. Okay, so with that, so if that angle deviates from that, there's going to be some strain associated with it. It's kind of like when your shoulder is wrenched out of position, right? It hurts, and the farther back it goes, the more it hurts. So with that, right. So with that, so the more the deviation, so the farther away you get from this 109 degrees, either the weaker the bond, or the more reactive it is. Okay, the more difficult it is to synthesize. Okay, so if you have a triangle here, right? So with that, so normally these carbon-carbon bonds, these regular carbon-carbon bonds, are going to want to be 109 degrees. Okay, because this carbon here has 4 groups around it, this group, that group, and then those 2 hydrogens. So it normally wants to be a tetrahedral shape with 109 degrees. Okay, but the real bond angle is 60 degrees. Okay, so this is way far away. So it's what, almost 150 degrees out of normal. Okay, so cyclopropanes here are incredibly reactive. Okay, or incredibly unstable. Okay, there's a lot of strain in there. Okay, same thing goes with cyclobutadiene, right? So each one of these carbons has 3 groups around it, right? The double bond, the single bond, and then the hydrogen. So that's this structure, right? The trigonal planar, which has 120 degrees, but the real bond angle, if you measure it, is 90 degrees. Okay, so again, you're out of bond angle by 30 degrees, something like that. And so so there's a lot of angle strain associated with this. Okay, so we're getting more and more. We're talking more and more about 3-dimensional structures. Okay, and so the way that we sort of denote that, okay, is with this wedge and dash notation. Okay, so with that, and so what ends up happening is, how do we do this? So if you have, if you have, say, a structure like this, okay, if the bonds are sort of just written normally, okay, so if you have just a regular line and a regular line, that means that they are in the plane of the board, or plane of the paper, plane of the board, okay? If it's coming out at you, okay, what it means is how we draw that bond there is a wedge. It's a very heavy line, okay? Okay, so this hydrogen is coming out at you, okay, and if it's going away from you, it's underneath the paper or underneath the board, we use a dash notation. So somebody said dash away. That's one way that you can remember it, okay? And so you sort of take a look at this. Let me see if I've got some balls to help visualize this. Okay. So these red ones, okay, these are going to be in the plane. Okay, the green is going to be behind, and the blue is coming out at you. Okay, and so hopefully little hard to see, sorry. Okay, but these red ones are going to be in the plane of the board. Okay, the blue one is coming at you, so that'll be on a wedge, and this green one is going away from you, and so that's going to be on a dash. Okay. Okay, so you can sort of think about this, and the model kit actually helps, right? So you have these two things, and they kind of come together, right? These are going to be in the plane. This is keep consistent with the other one. This is coming out at you. This is going behind, right? And they sort of come together like that. Okay. So play around with your model kit. Okay. So with that. So with that. So for here, right? So these hydrogens, or excuse me, these carbons are right in a row. Okay. These carbons are in the plane. Okay. With hydrogens around them. Okay, but this is the important one. See how that hydrogen is coming out at you. Okay. But that oxygen is going away, so that'll be on a dash. Okay, so if you want to do a skeletal structure, it would look like this. And again, they sort of talk about this in the book, but do if you get a model kit, one of them, it doesn't necessarily matter which kind you can. You know, this one is available in the bookstore. It's available on Amazon, stuff like that. So the most important thing you can do is to just play with it, to get used to it, to how the bonds are arranged, being able to make single bonds, being able to make rings, being able to make double bonds, triple bonds, knowing how to do that, stuff like that. So. Knowing what the different colored atoms mean. Typically, carbon is black, and the hydrogens are white. So like that, oxygen's sometimes usually red. The nitrogen's usually blue. The halogens are usually green. Stuff like that. So, but again, if you need help, come talk to me. Stuff like that. So I can help you through those. I've seen enough of these. But the best thing you can do is practice before the test, so you know what's going on with them. Okay, so this is one of the things we touched on in the last exam. Okay, so this is the issue with dipoles. Okay, and so with this, right? So we're talking about electronegativity, and the closer something is to carbon, or excuse me, to fluorine, okay, the more electronegative it is. Okay, and so and if you add the individual dipoles up, you get an overall dipole. Okay, so here there's just one arrow, so that means that the overall dipole is over here. Fluorine's more electronegative than hydrogen, so the dipole is going to be the negative charge is going to be on the fluorine. Okay, here carbon dioxide, right? You have equal and opposite dipoles pushing, so there's no overall dipole. But for water, right? So that the hydrogen or the oxygen is more electronegative than hydrogens, right? So they're gonna go towards the oxygen, and then both of those, if you add it up, go this way. It's going to be the negative charge is going to be on the oxygen, the negative character. Okay, so this overall, the red one here, again, is the overall dipole moment. Okay, and so we talked about this last time, but you just add them up. Okay. Okay. So next up, we're going to be talking about physical properties and functional groups. Okay, so the functional groups, right? So that was that list where I had you circle and name them. Okay, the reason why those are important is that's typically where all the chemistry happens, or is at those functional groups. Okay, and each functional group is going to have is going to impart slightly different properties onto the molecule. Okay, so with that, so we're going to talk a little bit about those forces. Okay, but the rule of thumb is for a lot of these things is the stronger the charge density. Okay, so the more negative and positive character you have on the atoms, okay, the stronger the intermolecular forces are. Okay, it's just, basically the bigger the charge, okay, the more they're going to attract. Okay, so like that. So, okay, so just as a reminder, we've got for melting and boiling points. Okay, so with that, so with solids you have a lot of interactions, right? So you have this competition between motion and intermolecular forces. Okay, so in solids, those forces are with that, so the are hopefully maximized. Okay, so that there's not a whole lot of movement. That's why it keeps its shape. As it melts and it becomes liquid, that kinetic energy is starting to build up. Okay, more heat in there, so that it's starting to be able to break away from those. From the forces, the molecules are able to break away, and then in gas, that's where you have a release, so you can break away from the individual molecular forces to be able to go out on your merry way. Okay, so with that, but again, the stronger the intermolecular forces, the more likely it is to be able to be wanting to get held together, the higher the melting and boiling points. Okay, so that's why it takes. There's a lot of intermolecular forces in holding water together. That's why it boils at such a high temperature. Okay, that's why it takes so long to boil water for the mac and cheese. Right, it just takes a long time because you have a lot of energy these forces to be able to break. Okay, so about that. So the more forces, the higher the boiling point. Okay, so the simplest bond, okay, is this ionic bond where you have the transfer between the two. Okay, and this is probably the strongest of the forces. Okay, that's why salt melts at such a high temperature. Okay, because you have a lot of these charge. Right, so with that, so you have a definite charge on the chlorine. Definite charge on the sodium, right? So, but it's a full charge. This bond is actually incredibly strong. Okay. So about that. So the next one are what are called dipole-dipole interactions, and what basically happens is instead of full charges, okay, they're going to be partial charges. Okay, and so if you have if you have hydrochloric acid in the gas phase, okay, what's going to happen is, right, you have a dipole here, right? Chlorine is more electronegative than hydrogen, right? So that chlorine is going to have a partial negative, and the hydrogen is going to have partial positive. But the way they align up, okay, is positive, negative, and between the molecules, right, the negative on this side is going to get attracted to the positive on that side, the partial positive on that side. So there's going to be an interaction between these two molecules, and this keeps going down the line. Okay, so there's going to be a lot of these chlorines going to be able to be attracted to the hydrogens, and a lot of hydrogens are going to be attracted to the chlorines, right? So with that, and the stronger this difference, okay, which right, so hydrofluoric acid, so HF, okay, you're going to have an even greater partial negative on this charge, okay, and so this attraction is going to be stronger, right, because you're going to have a larger negative charge and a larger positive character, larger negative character, and so this interaction is going to be higher. Okay. So hydrogen bonding is a sort of a special case with this. So it's still going to be a situation where you have, but it's just going to be working with hydrogens. Okay, so this one is in some ways sort of a hydrogen bond. So with that, but for here, what you have is you have a hydrogen. Okay, you have what's called a hydrogen bond donor. So it's a hydrogen atom on something that's electronegative. Okay, so carbon doesn't count. Some of that. So you're going to have something on electronegative. So nitrogen, oxygen, sulfur, phosphorus, something like that. Maybe the halides. Okay, it's going to have a right. So with that. So so if you have something like methanol, okay, it's going to have it. Right. So here you have a partial negative, partial positive. Right. So with that. So if you have another methanol molecule, okay, part negative, partial positive, right? This hydrogen is going to be attracted to the lone pair, right? Because it has a partial positive charge. It's going to get attracted to the lone pairs on this oxygen, okay? That's negative character to it, right? So you're going to get this, and this is called a hydrogen bond, okay? This is the donor because it can donate a hydrogen, and that's the acceptor. The thing with the atom with the lone pairs is going to be the acceptor. Okay, so dipole-dipole interactions is sort of a general case. Hydrogen bonds are where you're just dealing with hydrogens, stuff like that, and so these can be incredibly strong. Okay, they're weaker. They are weaker than ionic bonds. So ionic bonds are about as strong as you can get, but they're stronger than regular dipole-dipole interactions. That's why we talk about them specifically. So they're much stronger than regular dipole-dipole interactions. They're incredibly important in biology, okay? And so you have the two strands of DNA, in your DNA. So with that, so what's holding those two together are the hydrogen bonds between the bases of each strand. Okay, and so while each individual one is relatively weak, compared to an ionic bond, but they are fairly strong, and so it's incredibly, if you add up the millions, in an individual strand of the individual ones in a strand of DNA, they add up quickly. Okay, so with that, so they're important in DNA and RNA. They're important for getting proteins folded, right? So in here you got a alpha helix and beta sheet, the secondary structures there. There's a lot of hydrogen bonding that's holding those, that's forcing it to go to fold in a particular way. Okay, that's what's holding it together. So. Okay, so with that, so the more hydrogen bond donors and acceptors you have, the higher the melting and boiling points. Okay, and so for here, this molecule, right? So it has 4 hydrogen bonding donors, okay, and 2 acceptors. Each one of these nitrogens has a set of lone pairs. So overall, there's 6 of these things. On this one, there's only 2 hydrogen bond donors and 2 acceptors. So overall, it has 4. Stuff like that. And so this one here is going to have the higher boiling point, because it has more of them. Okay, not that this one's stuff like that. So for hydrogen bonding, again, the other thing you have to look at is the bigger the electronegativity difference between the hydrogen and whatever's binding to it, the higher the boiling point. Okay, so. And so for here, oxygen is a lot more electronegative than nitrogen, okay. And so this is going to have a higher boiling point, because this is oxygen's more electronegative. Okay, so induced dipole interactions. Okay, these are commonly called London dispersion forces, or just called dispersion forces. So this was just named after Fritz London, who discovered these. He was a Duke professor. With that, and he probably would have won the Nobel Prize, but he was killed in 1954 in an automobile accident. You can't get them posthumously. So with that, so the instantaneous, what happens is, it turns out that you have your electrons in here, okay, and so if for whatever reason they spontaneously come up to, say, one side of the molecule, what ends up happening is if all of a sudden, if the electron distribution is uneven, okay, now it sort of has a very slight dipole. Okay, it just happens that the electrons are over on one end. What that does is that actually repulses the electrons on the other molecule next to it, right? If this has a negative charge, it's going to push the electrons to the other end, right? Well, now this one has a dipole now. And so what happens is you get this sort of what's an induced dipole. Okay, so you have a positive, negative end, and on and on. So with that, now it's very quick, and it goes away. But it happens enough that that you get these interactions. Okay, so it's when one of it happens, you starts this cascade for all the other molecules, and so with that, and so that ends up producing a very small interaction. Okay, this is incredibly important with hydrocarbons. Okay, normally those hydrocarbons don't have a whole lot of interactions with each other. Okay, but this is what holds hydrocarbons together, particularly sort of longer chain ones. Okay, normally otherwise they wouldn't. Stuff like that, and so the ability to do this depends on what's called the polarizability, the ability to distort this electron cloud. Okay, so with that, so increases with increasing electrons in the molecule. Okay, so as you add more electrons into the molecule, right? So you add extra double bonds, triple bonds, things like that. You're going to get higher boiling points. Okay, because the more polarizable, the higher the boiling point. Okay, and it also one of the things that ends up happening is the more compact the molecule actually lowers the boiling point. So you want it to, if you want a higher boiling something, you want it to be stretched out. Okay, so with that, so which has the higher boiling, right? So each one of these, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Each of these has 7 carbons. Okay, but this one is stretched out more. Okay, this is much more compact. So the one that's stretched out is going to have the higher boiling. Okay, so with that, and so if you want something higher boiling, you're going to want to do a straight chain. If you want something lower boiling, you're going to want a smaller chain, or a more compact chain, a branched molecule. Okay, so with this, one of the things we're going to do with these interactions, okay, is talk about solubility. Okay, and we learn in Gen Chem, all right, so that like dissolves like. Okay, but we never answer the question why. Okay, so we say, well, we talk about polar, nonpolar, that sort of stuff. Polar molecules like polar molecules, dissolved in polar solvents, and vice versa, stuff like that. But we never actually tell why. And it turns out that what is actually happening is the disruption of these bonds or these interactions. Okay, if you disrupt the hydrogen bonding, okay, that's going to be a bad thing. Okay, so with that, and so if the only interactions you can get in the molecule are induced dipole interactions, right? The only things that you're going to be able to dissolve it are other things that have induced dipoles. If you have hydrogen bonds, okay, the only things that you're going to be able to dissolve in it are other things that can participate in this hydrogen bonding. Okay, stuff like that. And so if you have pure hexane, which only has induced dipole, and you mix it with water that has a little bit of water that has hydrogen bonds, when the water goes in, it's going to disrupt that hydrogen bonding. Okay, and so that's a bad thing. Okay, because those hydrogen bonds are very strong. Okay, and so this is not going to mix. So water and oil don't mix because you're breaking up the hydrogen bonding when the oil is getting in there. Okay, but if you have methanol, which has hydrogen bonds, and water, which again has hydrogen bonds, you mix those together, everybody's okay. Okay, because because they still can retain hydrogen bonding. Now, it's going to be different molecules, but that doesn't matter. Okay, so like that, and so what you want to do is you want to be able to keep the interactions that you have. Okay, if you disrupt those, bad things happen. Okay, and so here we go. So which compound is most likely to be soluble in water? Okay, and so this one here only has induced dipoles. Okay, now this one I made a slight mistake. This one pretty much just has dipole interactions. Now it does have a hydrogen bonding acceptor. Okay, because there are lone pairs here. Okay, so like that. So it does have a hydrogen. So that could be slightly soluble in water. Okay, but this one here, right? It has, not only does it have the ability to do has a hydrogen bond donor, but also has an acceptor. Okay, and so this one here, because it's most closely, it can do both donor and, with water you're going to have both donor and acceptor for hydrogen bonds. You're going to be able to maintain those, and so this alcohol here is going to be the most soluble. This one does have dipole interactions, but it also does have it also has a hydrogen bonding acceptor, so like that, and so that could lead to some additional solubility. But this is going to be the most soluble. Okay. Now with solvents, okay, so if you're going to want to dissolve ionic compounds, okay, so those are going to be obviously have charges associated with them. What you're going to want to do is you're going to want to have things that have dipoles, okay, so with that, so charges, things that have, they're going to be attracted to that, okay. So the rule of thumb is the increasing dipole of the solvents, the more likely to dissolve a salt, okay. That's just a rule of thumb, okay. So basically, ionic bonds are the strongest. So the strongest is going to be ionic bonds. Okay. Okay. Ion dipole is going to be middle, and then dipole is going to be the weakest of the three. Okay. So ionic bonds themselves are going to be the strongest. Ion dipole is going to be the second. All right, so this is 1, this is 2, this is 3. Okay, so hydrogen bonding H bonding is probably going to be here, and so dispersion is going to be here. These induced dipoles is going to be here in the sort of grand scheme of things. Okay. So what ends up happening is, right, so if you have this, in this case it's formic acid, okay, oop, negative charge here, okay, so see you have sodium formate, okay, what's going to happen is with your water, right, so this part's your water, right, this is going to be the positive side, negative side, okay, it's going to be attracted to this part of the ion, right? So with that, but for the sodium, right, it's going to get attracted like that, right? See, the negative side and the positive side, I should say. These are partial. Okay, the partial in this case, the partial positive is going to get attracted to the negative ion. The partial negative side is going to get attracted to the positive side, or the positive ion. Okay, not too bad. But it's not just one. It's there's actually going to be a whole lot of them around there. Okay, and it's going to say that it's solvated. Okay, they're going to have a whole bunch of these things around. Okay, and so they're going to actually get separated. Okay, you're going to be near each other. Okay, but you're going to have solvent around there, and it's a solvent cage. Okay. Now, so again, for hydrocarbon length and solubility, okay, remember the hydrophobic is water loving, hydrophilic is water loving, hydrophobic is water fearing, okay? As you increase the carbons, okay, that decreases the water solubility, okay? So as you increase the number of carbons, okay, those dispersion forces are going to become more and more important, okay? And so if you have something like heptanol, which has 7 carbons, even though you can participate in hydrogen bonding here, okay, with water, okay, there's so many more dispersion forces that it's going to disrupt that, okay, that's able to overcome, okay. So what ends up happening is, if you there's a sort of a water solubility ratio. So if you have, for carbons, if you have carbons to hydrophilic functional groups, if there's 3 or fewer carbons for every hydrophilic functional group, then it's going to be soluble in water. Okay, if you have greater than 3, then you're going to drop solubility. Okay, it's not going to be completely soluble. Okay, so for here, okay, so for this molecule, right, so we have so we have these molecules, okay. Okay, so we're going to say from many carbons to functional groups. Okay, so for here you have 1, 2, 3 carbons. Okay, 1 functional group. Okay, 1, 2, 3. Here you have 1, 2, 3, 4, 5, 6. Okay, so 6 carbons, right? 1 functional group. Okay, here we have 2 functional groups. Okay, and then 1. Oop, I missed a carbon. Oops. There's 2 functional groups, 1, 2, 3, 4, 5. Okay, and so if you look at the ratio, it's 3 to 1. Okay, this is 6 to 1, and this is 5 to 2, which, if you simplify it, ends up being 2.5 to 1. Okay, so which ones are going to be soluble in water? It's going to be that one, because it's less than 3 to 1, right? It's 2.5 to 1, and this one. Okay, so those 2 are going to be the ones that are soluble in water. This one, there's too many carbons in there. Okay. So it's going to be less soluble in water, right? And so if you look back here, right, that's hexanol. It's only oops, sorry, I marked on my screen. It's only less than 1. It's about 6 grams per liter. It's very insoluble. Okay, especially consider how about that. So, okay, so this is a nice little calculation to be able to do. Okay, the book goes into this thing of ranking boiling points and solubilities and things like that. This is way too complicated. We've got bigger fish to fry in this thing. If you want to take a look at it, feel free to. I'm not going to ask you about this. It's going to be relatively simple like this. So with that, I figure if you can get this part, you could probably work it through. Okay, but I mostly just wanted to look at the basics of this. Okay, now, right. So with that, so the next thing to talk about with solvents, okay, is we're going to talk about what are called protic and aprotic solvents. Okay, so the reason they're called protic, okay, so if you think about like an H plus, okay, so right, so we have protons, right, so we have protons electrons, and neutrons. Okay, so how many protons does a hydrogen have? Right, it has 1. Okay, for an H plus, right? So how many electrons does it have? It actually doesn't have any. All right, so it normally would have 1, but you've stripped it away to make the H plus, and so it doesn't have any. And for neutrons, right? So a hydrogen doesn't have any as well. Okay, so an H plus molecule is pretty much just a single proton floating around. Okay, so and what's ends up happening is this has sort of become an abbreviation, sort of a nickname for pretty much any hydrogen. Okay, it's called a proton. For so that it comes from the fact that an H plus is just a single proton floating around. Okay, and so with this, okay, so what ends up happening is you hear these things about protons. Okay, for here, so protic. Okay, so what that means is that it has a hydrogen. It has a hydrogen bond donor. Okay, and so what that means is it has a hydrogen on something electronegative. Okay, so it has an OH, it has an NH, it has an SH. Okay, those are all considered what's called protic solvents because it has a proton on something electronegative. Okay, aprotic solvents don't. Okay, so for here, right, this is an OH. Or say you have a hydrogen on that oxygen. Same here, hydrogen on that oxygen. Acetic acid, we have a hydrogen on that oxygen. Okay, all of those are going to have are considered protic solvents. Okay, so if you had, methyl mercaptan. Okay, this is what makes they add into natural gas to give it that scent. Okay, it smells like rotten eggs. Okay, this guy here, right, is an hydrogen on a sulfur. Okay, and stuff like that. And so this is a protic solvent. Okay, aprotic solvents don't have that. They just pretty much have the hydrogens on the carbons. Okay, so DMSO, dimethyl sulfoxide, right? All the hydrogens are just on carbons. Again, acetone, DMF, and then dimethylformamide. Okay, that is again all the hydrogens are on carbons. Okay, so those are considered aprotic solvents. Okay, the reason why we're talking about this is that down the road we're going to be talking about reactions, and some work better in protic solvents, some work better in aprotic solvents, and stuff like that. And so it becomes down the road it becomes important. Okay, so for aprotic solvents, so protic solvents work really well generally, particularly small ones for dissolving salts. They work pretty well. Water is actually is obviously fantastic for dissolving most salts. Now there are some that are insoluble, but we won't worry about that. Okay, the problem with aprotic solvents is actually an issue of sterics. So they're not great at dissolving salts. Okay, so the negative end can get into that. So if you had sodium chloride, the negative end is pretty good. Okay, so if you had sodium, okay, for something like DMSO, right, it's gonna look. So for here, this is the negative end. This is the positive end, right? It can get really close to it. Okay, the problem comes if you have a chlorine atom or chloride. Okay, it's going to have to get. This is the polar. This is really where that positive charge or that partial positive resides, and the problem is it's going to have to. These methyl groups here are bumping into that chloride. Okay, well these things don't like to be next to the charge, right? So it's kind of trying to squish that in there. There's just a lot of distance between here, and so it can't solvate these chlorides very well. Okay, it can do the sodiums pretty well, but not the anions. Okay, and stuff like that. And so this becomes a barrier. Okay, and stuff like that in order to be able to dissolve salts. So DMSO isn't great at dissolving salt. Like that. So, okay, the last one we're talking about are soaps and detergents. Okay, and so typically what ends up happening is you get you need two parts. You need a long hydrophobic tail, okay, here, and then you need what's called an ionic head group, okay, a polar head group. Okay, so here this is SDS. Okay, so you're going to use this if you do anything in molecular biology. This is a typical one in regular shampoos, stuff like that, and so this is a typical one. One, if you make lye soap, is going to look like this, okay, stuff like that. So with just a carboxylate, carboxylic acid that's been ionized, stuff like that. This is a classic one, stuff like that. So that was made for centuries. The way these things work, okay, is in water, right? So this one here, this is going to be very happy by water, right? Because it's ionic, right? So it's going to want to be around the water molecules. But here you have all these London dispersion forces, okay? This can't hydrogen bond, okay? And so what ends up happening is they self-assemble, so that all the sort of greasy parts, all the hydrophobic parts are in the middle, and then all the head groups are outside. So it sort of forms a capsule. Okay, so that all your hydrophobic groups are on the outside and all your grease is on the inside. Okay, and so you can sort of see it here. All the head groups are on the outside. All the water molecules are on the towards the water molecules, and then all of the grease is on the inside. Okay, and what ends up happening is, right? So if you have a stain, okay, everything that's water soluble is just going to go into the water, no problem. Okay, but if you have a greasy stain, okay, what's going to say is it doesn't want to be in the water either. Okay, but when one of these, they're called micelles, one of these micelles bumps into it, the grease is going to say, ooh, there's a greasy environment in the middle of this thing. I want to go in there. Okay, and so what ends up happening is it transfers itself inside that micelle. Well, the micelle itself this capsule will float around the water, and when it'll stay within the water, and then when you flush away the water with the soap in it, away goes the grease. Okay, so with that away from your clothing. Okay, and so that's how these soaps work. The problem is if you have hard water. Okay, so with that, and so with hard water, if you have let's say a lot of clay, so that you have high calcium and magnesium concentrations in there, and this is where you get the soap scum. What ends up happening is, particularly for soaps like this, they can react with the calcium and magnesium and form insoluble salts. Okay, and so this is not soluble in water. Okay, so that's why we've switched to things like SDS. Okay, is because they're less likely to form these insoluble salts compared to the older older detergents that were made from lye. Okay, so with that, and so now you don't have nearly the soap scum that you did before. Okay, so with that, okay, good luck.